think we should start. So, hello everybody, welcome back. Let's see. Should I? Yeah, let's just. Oh, okay. First of all, homework number 1 is due next Wednesday. And then, yeah, let me know if there's any questions on the homework, by the way. Due next Wednesday on grade scope. If you haven't gotten an email from Gradescope, then let me know. I'll send you an invitation. Okay, so last time I defined cluster algebras. And the definition was that you'd start with a seed x tilde comma q, and then you mutate in all possible ways. So you mutate all the mutable vertices, you get a bunch of quivers, you mutate all of their mutable vertices, you get a bunch of more quivers, and etc. And then the cluster algebra A of x tilde q is generated as a ring by all the kind of cluster variables you get as you mutate, by all cluster variables together with inverses of frozen variables. Right, and so what we discussed last time was that if I take T a triangulation, and then so from here I get a seed, the usual one where you label the diagonals by Pij, and then from here I get a cluster algebra, which, as we discussed last time, this cluster algebra is not isomorphic to the coordinate ring of the Grassmannian. Grassmannian of 2-dimensional planes inside the n-dimensional space. And just to remind you, the coordinate ring of the Grassmannian is just you take C, the polynomial ring in the Plucker coordinates, modulo the Plucker ideal, which for Grassmannian 2n is generated by only one type of relations, ACBD minus AB, PCD minus PAD, PBC. And so it is not isomorphic. And the reason was that inside here we have inverses of frozens, but inside the coordinate ring of the Grassmannian we don't, because those are not, they don't give you polynomial functions on the Grassmannian, the inverse of Plucker coordinates. And so the kind of the standard thing to do in this case is to not just, okay, first of all, any questions? Any questions so far? Sure. Right. Where in general, right? So okay, in general, let me in all possible ways. So in general, you get infinitely many quivers, and even more, like many quivers may give you. A single quiver may give you, like if you mutate a quiver and somehow you go back to the same quiver, you may get a different seed. So you get infinitely many quivers and infinitely many seeds and infinitely many cluster variables. But for when Q is a path quiver, then you get finitely Okay, then you get finitely many of all those things. So finitely many quivers and seeds and etc. And the reason for that is that they correspond to triangulations. Right. So in a triangulation, you can mutate any diagonal, and so no matter how much you mutate, you always stay inside the set of triangulations. Was that all right? Okay, thanks. Yeah, that's, I mean, and that's actually going to be like one of the main objects of study for the next like 5 lectures. You know, which ones are infinite and which ones are finite. And that's a non-trivial question which I'm gonna discuss in depth. Any other questions? All right. Okay, so here's what I want to say. Whenever you have the coordinate ring on some algebraic variety, and then you want to invert some functions which are not invertible, the usual thing to do is to just remove the set where the corresponding functions are 0. Just kind of get rid of those points, and then you get a new kind of open subvariety where, yeah, I'm saying all these words, but it's all very simple. So let me just define. The corresponding subvariety, and I'm gonna do this for general Grassmannian. So consider general K. I mean Grassmannian K, comma n. Right. So these correspond to like row spans of full rank K by n matrices. And then what I'm going to do is I'm going to consider n sets. I'm going to consider all cyclically consecutive K element sets. I1 is 1, 2 up to n, up to K. I2 is the set of 2, 3 up to K plus 1. And so I keep going until it wraps around. So the last one is going to be In, which is n, 1, 2 up to K minus 1. Okay, and so for the case K equals to 2, I get, I1 is 1, 2. I get 1, 2, 2, 3, etc. up to n minus 1, n minus 1, comma n, and the last one is going to be n, comma 1. So these are exactly the sides, the labels of the sides of a polygon. All right. And so then I define the, okay, so this is going to be an important definition. And it has a long name, unfortunately. So the top open positroid variety is denoted pi circ K comma n. It's basically you just take the Grassmannian and then you remove the set where at least one of these Pulliker coordinates vanishes. So it's given by p pi k n is given by the set of all elements of the Grassmannian, where delta I sub r of v is non-zero for all r from 1 up to n. So for all of these sets, I remove the corresponding Pulliker coordinates are required to be non-zero. And so, well, I mean, and then kind of the theorem, which is kind of an easy consequence of. So last time I explained that if you forbid the inverses of Rosens, then you get the coordinate ring of the Grassmannian, and from here it's not hard to see that the coordinate ring of pi kn is isomorphic to the cluster algebra corresponding to a triangulation, where so the coordinate ring of this guy is just you just add pi1 up to pin. Just add inverses of these Flickr coordinates to the generators. That's a general procedure. Like whenever you restrict to a subset where something is non-zero, then this function is allowed to be inverted in the coordinate ring. So anyway, so far this seems like I'm saying something pretty like straightforward, and it's true. But so okay, first of all, later we are going to see there is going to be so open. Okay, open just means that these things are non-zero, and top means that there will be other kind of lower dimensional positroid varieties. And so for each of these lower dimensional guys, this theorem is going to be true, right? So its coordinate ring is going to be isomorphic to some cluster algebra, some kind of very nice cluster algebra. But the previous result, where you take the closure and then you remove the frozens from the generators, it's still an open problem. So all right. So right now I don't want to talk too much about this, but that's just kind of a preview of what's going to be towards the end of this class. And so this positroid variety pi sur kn is also going to be the one that's related to, I don't know if you saw the syllabus, but it's related to all kinds of very exciting stuff like Qt Catalan numbers and knot theory and etc. So there is a whole bunch of exciting things which you don't see if you just work with the Grassmannian. So somehow the Grassmannian, even though this guy is obtained from the Grassmannian by removing some kind of a bunch of hypersurfaces, these hypersurfaces are so nice that somehow you recover all that interesting stuff, which I'm going to explain. But so far I want to focus on this. Well, okay, yeah, I guess this lecture is a little bit like an overview of what we did so far and what's going to happen next. So it's going to be not a lot of content mathematically, but there is going to be, I just want to give you some context of what was going on when the cluster algebras were invented and stuff like that. And so let me pause for more questions. No, I will say that there is a very nice answer for that. Yeah, yes, I will. That I will explain. Yeah, I'm sorry. I mean, I wanted to give you a preview, but I certainly don't want to talk about this at this point. So if this is, I understand that this is not completely clear, but it's going to become much more clear later. All right. Any other questions or comments? Okay. So what I want to discuss today is motivation for cluster algebras, and by which I mean kind of historically, because later they got connected to all these other interesting things, but originally there was kind of two main motivations. So two reasons due to which cluster algebras were introduced. The first one is canonical basis. Canonical basis. and the other one was Zamolodchikov periodicity. And so let me expand on these two things. First, so for the canonical basis, I guess the main paper is this paper by Lustig. So canonical basis. So you should read the paper of Lustig from 1990. And basically, so he introduces these, quantized enveloping algebras. Basically, you just, whenever you have a Lie algebra, it has representations, and then inside of those representations, you want to choose some kind of basis with nice properties. And so he managed to do that. And there were some kind of very nice positivity properties, and he showed that there is a unique basis satisfying such nice properties. And so that was a big result back then. Yeah, you can see the journal, the same journal again. And so that was, and so cluster algebras were an attempt to understand his canonical basis combinatorially. So yeah, let me mention that in particular, this construction gives a nice basis of the coordinate ring of the Grassmannian. So all these coordinate rings of the Grassmannian and the flag variety then can be identified with certain representations, and then so Lustig gives the canonical basis. And so how do you get a basis from a cluster algebra? And let me actually mention a nice conjecture here. So yeah, here's the definition. Let's say I look at some cluster algebra. And so by definition, a cluster monomial is a monomial in the variables of a single cluster. Right. So you start with your initial seed x tilde q, then you mutate some number of times, and then you get some other seed x tilde prime q prime. And so if x tilde prime is x1 prime all the way up to xm prime, then you can get a cluster monomial, the form like x1 prime to a1 times x2 prime to a2, etc. xm prime to the am, where all the ai's are non-negative. And yeah, of course, you can also add the inverses of Frozens. Yeah, there's a let's only take the cluster variables. So instead of m here, I'm gonna write n. So I only want to talk about the cluster variables here, right? So whenever you find any, let's say, triangulation, and then you can multiply the Pulkar coordinates for that triangulation as many times as you want, and you get a whole bunch of functions on the Grassmannian, let's say. And so the conjecture that, well, first the theorem that it was conjectured originally by Fomin and Zelinsky, but now it is a theorem, is that cluster monomials in any cluster algebra are linearly independent. So so for example, for example, if you look at like P13 times P24, if you look at the Plicker relation, P12 times P34 plus P14 times P23. I guess I'm doing the frozen ones again, but whatever. Like these two are cluster monomials, but this one here, this is not a cluster monomial because you multiply things from different clusters. P13 and P24 never belong to the same cluster. And so that's kind of a linear relation, but it does not contradict the theorem. And that's kind of a very nice, because so Lustig's construction is very algebraic and very not really like that explicit. But this is very explicit. Start with a quiver, you mutate, and then you take all those things, in like all the monomials, and you get some linearly independent set. And hopefully sometimes you get a basis. So maybe you always get a basis or not. And so yeah, I think I should mention, okay, there is a paper with a lot of authors which proved the linear independence of cluster monomials. Yeah, proved this theorem basically. And so a question that is not completely solved at this point. So question, or a problem, which is find a basis of a cluster algebra containing all cluster monomials. And so yeah, hopefully there is like several questions. First of all, does Lustig's basis contain all cluster monomials? And second of all, can you find a basis? And it turns out that there is. So the answer to this question is not completely satisfactory. So here I mentioned some other paper, and the one it has appeared in these lectures before. So these Gross, Haken, Kilk, and Savage, GHKK 18, they construct a theta, what is known as a theta basis, which, yeah, I'm not going to explain, but anyway, the point is that everything is non-clear in this. Even though this was the original motivation, to this day, the situation is not completely resolved on that. But still, historically, this was kind of the motivation was to understand these canonical bases from a combinatorial point of view. And there has been a lot of research, but still the relation is not completely understood. All right. I guess that's all I want to say here, so any questions? All right. Yeah. Okay, so you can take, let's say you take a general linear group, and you take a representation of that group. So that means you look at some linear space where this group is acting, and then out of all representations you want to choose the irreducible ones, and the irreducible ones correspond to very nice objects. So irreducible representations of, first of all, there is the symmetric group, or of the general linear group. They all correspond to basically Young diagrams. Young diagrams, where a Young diagram is just a weakly decreasing sequence of integers. These are all integers. And so, okay, and so you have this irreducible representation of, so it's a finite dimensional space on which Sn or like GLN acts. And inside of GLN you have these diagonal matrices. And so diagonal matrices form an abelian subgroup, so they act by basically the whole, this irreducible representation, it decomposes as a direct sum of eigenspaces for the diagonal matrices here. And inside of each eigenspace, you want to choose a basis such that certain kind of I mean, this basis has to be like upper diagonal. Anyway, it has to satisfy some nice properties with respect to the action of these matrices here. Like you can choose a matrix which has ones on the diagonal and then some t above the diagonal. And so say it again. Yeah, okay. Yeah, I know it is not satisfactory, and yeah, it will take me a whole class to explain this properly. First to kind of yeah, anyways. I mean, that's a good question, but unfortunately there is a lot of stuff that goes into this construction, which I will try to keep. I want to keep this class kind of more elementary, and so. All right, let me mention the. Basically, I'm not going to talk about the first motivation anymore, but I am going to talk about the second motivation. Motivation number 2 is this Zamolodchikov periodicity. So yeah, here's, I guess there's a few papers. So okay, what did I say about Zamolodchikov periodicity? Nothing. All right. So Zamolodchikov periodicity, it's a certain. It was a conjecture. It was conjectured by let me write Zam 91. So by this basically physicist in 91 in relation to some thermodynamic beta ansatz. And so there's some kind of dynamical system was periodic. And so this conjecture includes the periodicity of Friese patterns as a special case. So the same kind of, remember we had these triangles and Friese patterns which went like this, and so Zamolodchikov basically conjectured the same thing happens for every Dynkin diagram. You have a homework about Dynkin diagrams, and so this conjecture originally was defined for a single Dynkin diagram and then was generalized for pairs of Dynkin diagrams. And anyways, this conjecture was proved using cluster algebras, proved by Fomin-Zelevinsky in 2003. So there's Y systems and generalized octahedra. So we're going to discuss this. We're going to discuss these things. And so proved for single Dynkin diagrams and more generally by Keller in 2013 for pairs of Dynkin diagrams. And again, you can see annals and annals here. And so, so that motivation was successful. Cluster algebras are exactly suited to solve this periodicity conjecture, and this is also closely related to the classification of finite type to this question of whether when you mutate you get infinitely many things or finitely many things. And so yeah, so and now I think I should explain the kind of what I mean by cluster algebras of finite type. And so now I'm going to slowly kind of transition into periodicity. And then, I mean, I'm going to explain Dynkin diagrams and stuff like that later. But for now, let me explain what's the problem. So, cluster algebras of finite type. Okay, what is a cluster algebra of finite type? And turns out there's two different notions. Remember, I was talking about if you get finitely many quivers or finitely many seeds, these are basically two different notions. Like one, of course, a seed is a pair, a quiver, and some labeling of the quiver. So finitely many seeds implies finitely many quivers, but in general, these notions are different. So let me state this all carefully now. So definition. Let's say I have two quivers, Q and Q prime. Then I say Q and Q prime are mutation equivalent if, I mean, that's the obvious notion, if they are related by a sequence of mutations. And so I'm going to denote by brackets Q the mutation, basically the equivalence class of Q. All right. And so, and then I'm also going to be, remember, a quiver an ice quiver has like frozen variables and mutable frozen vertices and mutable vertices, and so sometimes I'm only going to talk about somehow frozen vertices are not going to be too important for me here. So let me denote by Q mut the mutable part of Q. So that's the sub quiver of Q, which is so I only take the subset of all mutable vertices. So I delete all frozen vertices, and then the rest is called Q mut. And okay, now here are the two definitions. All of this should not come unexpected to you. So a cluster algebra A of x tilde comma q is said to be of finite mutation type if the mutation class of Q mut is finite. Right, so if you can get finitely many, so you forget about the frozens, and then if you can only get finitely many things from Q mut, then it's finite mutation type. Yeah? Yeah, that's actually a good question. Yeah, I'm gonna ask this question to you in 10 minutes. Yeah, so while you're listening to me stating 5 definitions in a row, you can think about whether including frozens makes things worse or not. And the answer is yes. The answer is yes, it does. Sometimes you get sometimes it may become infinite once you include frozens. And so the other definition is that the cluster algebra is of finite type if it admits finitely many seeds. Yeah. And so the basic question is basically, well, first of all, let me mention this paper. So cluster algebras of finite type have been all completely classified. By Fomin and Zelinsky in 03. And the classification is nice. And I'm going to explain it later. But now, so yeah, the basic question is like which are finite type and which are finite mutation type. These are also basically classified. So, but there's, anyways, let me first state a nice property which distinguishes finite type from finite mutation type. So proposition a of x tilde, whether this is whether a cluster algebra is of finite type depends only on Q mut. Depends only, first of all, yeah, you can choose the seed and then you can choose the quiver, the ice quiver, but whether it's a finite type or not is only going to depend on the mutable part of your quiver. And that's a non-trivial result. So you can add a lot of frozens and then yeah, let me actually consider some examples. So let's say, can you tell me some examples of a cluster algebra that's of finite type? Yes, thank you. Right, so an example is where Q is a path, then A of x tilde comma Q is of finite type. And so if you, like an example where you have a quiver, a path of length 2, A and B, and then if you mutate in all possible ways, yeah, first of all, yes, what do I want to say? Basically, yeah, I mean you get Catalan many quivers from that, but if you add the frozens, you still get Catalan many quivers. So let me this is actually interesting. Let me forget about the seeds and only talk about quivers for a while. So let's say I add a frozen vertex, and then let's say I add 2 arrows to one vertex, or something like this. And then let's say this vertex 1, this vertex 2. So if I mutate it at vertex 1, I'm gonna create 1, 2, let's say this is 3. So what are gonna be the new arrows? Could you say it again? Okay. Right. And so then if you I guess I should also do. Okay. And now if I mutate 1 again, I get back to here. But if I mutate 2, I'm gonna get something interesting. Right. 1, 2. What do I get if I mutate vertex 2 again? Vertex 2. yeah, okay. So, okay, you get something like this. And then, well, the only other one you can do is mu1. And you can see that it's basically a kind of symmetric to this. So the whole process is kind of is going to keep going. Yeah, this quiver is isomorphic to this quiver, except that you reverse all the arrows. And so as you keep going, you don't you get finitely many quivers. Do you agree or disagree with this? All right. And so now let's consider another example. Let's say I have another example where my quiver has 2 arrows from 1 to 2. This is called the Markov quiver. So first of all, is it finite mutation type? Yes, thank you. Okay, now here's another question. Is it finite type? And yeah, based on my tone of voice, you may guess that the answer is no. But okay, what do you think? Is the answer yes or no? Yeah, thank you. Yeah, that's actually correct, right? So if you, so the answer is no, and there are, well, first of all, an easy way to check it is to use this proposition, because if you add, let's say you have 1 and 2, and then you add a double arrow, and then you add a frozen vertex, 3, even if you start with 1 arrow, if you mutate here, you're going to get 2 arrows from 3 to 2. And if you mutate again, you're going to get like 4 arrows, which are going to cancel with the 1. Yeah, anyways, there is going to be, you get, if you keep mutating, you get infinitely many quivers. Is that okay, or should I do some number of mutations to see that it gets infinite? Okay, I see thumbs up. All right, yeah. I mean, I can do a couple maybe. Yeah, okay. Let me do another check, which is by definition. Right, we have a definition of whether something is finite type or finite mutation type, and so kind of if I don't want to cheat, I would start with a seed. So start with a seed, let's say x1 and x2, just some kind of arbitrary variables, and then as I keep mutating, I should check that I get infinitely many different seeds. But instead of starting with arbitrary variables, let me just set x1 equals to x2 equals to 1. Right, because then, so that's a weaker test, right? But if there's infinitely many things, even with starting with all ones, then of course there's going to be infinitely many seeds, right? And so what happens if I start with, I start with my quiver labeled by 1 and 1. And so what happens as I mutate, let's say at vertex 1? What are the values? 1 and 2, like 2 and 1. All right, what's the next one? Uh, 2 and, actually, 2 and 5. Okay, right, because as I mutate, I get 1 is replaced with 2 squared plus 1 over 1. So that's a 5. Because there's 2 arrows, I have to take 2 squared. All right, I get, yeah, let me distinguish the quivers from the mutations. All right, what's the next one? 13 and 5. Nice. What's the next one? Okay, 13 and 34, looking like Fibonacci numbers. Okay, that's interesting. Okay, can you give me the next one? Wait, did you? 89. Okay, 89 and 34. Wait, am I? Hold on. Yeah. Okay. All right. So 89 and 34, and so indeed, if you look at Fibonacci, so basically, well, let me write it down correctly. So you get a sequence x0, x1, etc., which is defined by recurrence relation xn plus 1 is equal to xn squared plus 1 over xn minus 1, or something like this. And somehow magically, the sequence gives every other Fibonacci number. Right, so Fibonacci goes 1, 1, 2, 3, 5, 8, 13, what is it, 21, 34. And so indeed you get 34, 13, 5, 2, 1. And so that's interesting, right? Somehow Fibonacci numbers are known to satisfy a linear recurrence instead of a. This is not a linear recurrence here. It's, you have a quadratic polynomial on top and you divide by xn minus 1. But somehow so okay, here is a question. Does this sequence xn satisfy a linear recurrence? Yes. Okay. Can you tell me which one? Or can you tell me why? Okay. Okay, yeah, that's true. That's a general fact. If you take a linear recurrence and you take every second term, then yeah, that's actually, I mean, that's not completely trivial to see for general recurrences, but here, yeah, the answer is yes. And okay, can somebody tell me the recurrence? 34, 89. Could you say again? Minus xn minus 2. Okay, yeah, I think that's the correct one. So 89 is equal to 3 times 34 minus 13. No, wait, what? Okay, all right, yeah, okay, good. yeah. So, okay, what am I trying to say? I'm trying to say that I guess some quivers are finite type, and some quivers are finite mutation type, and that's it. And so, question is, how do you classify these, and how do you classify those? And so that's what we're going to discuss in the next few lectures. And so that's it. And thank you very much. If you have any more questions, let me know. Yeah. Well, so whether quiver is a finite mutation type or not depends on depends on whether you add frozens or not. So if I start with if I only take this quiver, then it's finite mutation type, right? If I mutate this vertex or this, so kind of the mutable part of this quiver, is finite mutation, has finitely many quivers. Yeah. Yeah. So so by definition, the corresponding cluster algebra is a finite mutation type, but it is not of finite type because it has infinitely many seeds. Right. So I'm wait. Are you saying infinitely many quivers here, right? Well, okay, infinitely many ice quivers, but the point is that if you only look at the, so here you can see I'm taking Q mut, the mutable part, and I'm taking brackets, which is mutation class. Yeah. Yeah. All right. Thank you. Yeah. Yeah. Well, so I start with some initial seed. So right, yeah. So I'm allowed to fix a cluster algebra. So when I fix the cluster algebra, I guess I just fix one of the seeds, the initial one. But then, so the definition is asking whether, as I keep mutating, do I get infinitely many things or finitely many things? Coefficients not in C. Oh. Could you tell me which problem is it? Okay, so the sum is 4. You're right. So, well, basically, I think it should be solvable by just using. So you guess a quiver for the sum is 4 sequence, and then so the coefficients should come from adding frozen variables to that quiver. Does that? Yeah. Well, actually, that is a theorem. I'm surprised you need to use that theorem to wait. Am I? Let me look it up. Can you sum is 4. Do you remember the number of the exercise? Okay, coefficients in Z, A, B. Okay, then I guess I screwed up a little bit. Right, you need to use the stronger version of the Laurent phenomenon here, which is that the frozens don't appear in the denominators of your. Yeah, that's okay. Which theorem is that? Yes, theorem 336. It's the sharpened version of the Laurent phenomenon. Yeah, I'm gonna send an email about that. Thank you.